First of all, I'd like to thank everybody for attending this telecom seminar, one more telecom seminar, which is hosted by the Technology Innovation Institute at TII in Abu Dhabi. I am Dr. Daniel da Costa, currently a principal researcher at TII. And for today, it's a big pleasure and honor for us to have Professor Robert Schober as the speaker of this telecom seminar, whose talk will be entitled Modeling and Optimization of Intelligent Reflex Surface from RF to Optical Frequencies. Actually, I'm confident most of you know Professor Robert Schober very well. Actually, he needs no introduction. He has a brilliant career, and not only in terms of high quality research papers, but also due to his strong involvement with technical societies and activities. So his CV is indeed very impressive and extensive, but let me try to summarize his biography before moving to his talk. So Professor Robert Schober received the diploma in the PhD degree in electrical engineering from the Friedrich Alexander University of Erlangen-Nuremberg, Germany in 1997 and 2000 respectively. From 2002 to 2011, he was a professor and a Canada Research Chair at the University of British Columbia in Vancouver, in Canada. And since January 2012, he is an Alexander von Humboldt Professor and the Chair for Digital Communications at FAO. His research interests fall into the broad areas of communication theory, wireless and molecular communications, and statistical signal processing. Professor Robert Schober received several awards for his work, including the 2002 Hans Mein-Leibniz Award of the German Science Foundation, the 2004 Innovation Award of the Vodafone Foundation for Research in Mobile Communications, 2006 UBC Killen Research Prize, 2007 Human Fridge Besser Research Award of the Alexander von Humboldt Foundation, 2008 Charles McDowell Award for the Excellence in Research from UBC, in 2011, Alexander von Humboldt Professorship. 2012, NSERC EWR Stacy Fellowship. 2017, Wireless Communication Recognition Award by the Wireless Communications Technical Committee. In 2021, ACM Award by ACN Nano Milestone Award for fundamental contributions to the modeling, design, and analysis of molecular communication systems. Since 2017, Professor Robert Schober has been listed as a highly cited researcher by the Web of Science. He is a fellow of the Canadian Academy of Engineering, a fellow of the Engineering Institute of Canada, a fellow of IEEE, and a member of German National Academy of Science and Engineering. He served as editor-in-chief of the IEEE Transactional Communications from 2012 to 2015. And as a VP publications of the IEEE Communication Society in 2020 and 2021. And currently he serves as the member of the editorial board of the proceeding of IEEE, member at large of the Consort Board of Governors, and as a Consort Treasurer. So Professor Robert Schober, thank you once again for accepting our invitation. And now the floor is yours.
Yeah, thank you, Daniel, for reading out my long biography. I think the long biography just means that I'm very old, right? I mean,
try to summarize
the older
it.
the older you get, the longer it gets, unfortunately.
Yes.
Right? Yeah. So thanks a lot for that. Yeah. So I would also like to thank Daniel and the other organizers for inviting me to give this talk. So that's a very nice opportunity for me to present not only my work, but really more the work of my students and postdocs that are listed here. So Marcie, Hetje, and Dongfang are my current students, and Wahid and Alex, they were postdocs at my institute, and they're now professors themselves. So the title of the talk, as you can see, is on intelligent reflecting surfaces. And of course, there's been, there's a lot of work on these surfaces now. So here I would particularly like to look a little bit at the modeling and optimization and the related problems. And also I would like to highlight a bit the role that the operating frequency of the system plays. So here's the outline of the talk. So I will start quite broad to give some background and context for those of you who are not that familiar with these surfaces. So sort of a gentle introduction. Then I will look at the modeling both at RF frequencies and at optical frequencies, and investigate what are the commonalities and what are the differences. And then move on to the optimization part, where most likely I will not be able to fully cover both of these sections because we will run out of time. But I will give you sort of the main idea, and then if you're interested, make the slides available afterwards so you can have a more detailed look. Okay, so let's have a look at some of the general concepts. So wireless communications has come a long way, right? So you can say it started with Marconi's experiments more than 120 years ago. And since then, it has become really ubiquitous, right? So it started with the cellular concept in the 1980s, and then the different generations of mobile communication systems evolved, and we moved on from one generation to the next. And the system and services that were provided, they became more and more advanced and more fancy, right? So, and today we all have a smartphone, and it's really amazing what these devices can do individually, but also sort of jointly with the entire network. Now, across all these generations, one thing that has not really changed is the abstract and fundamental building block of such a communication system, which is basically has three components: a transmitter, a channel, and a receiver, if you break it down. Now, over the generations, what we have changed and modified mostly is the transmitter and the receiver. So at the transmitter, we came up with more and more efficient and sophisticated coding schemes, beamforming schemes, resource allocation schemes, and so on. And likewise, at the receiver, we came up with more and more efficient decoding, interference cancellation, and channel estimation schemes. So those are the parts that we have modified up to the 5th generation. Now, the part that has not really changed over the different generations, that is the channel. So the channel we have generally accepted as being God-given, and we have not really tried to optimize it, at least not in a sophisticated manner, right? Of course, we have tried to place the base stations in convenient locations, so you could say this is like an optimization of the channel, but not in a really intelligent and adaptive manner. And this can have some serious consequences, as is illustrated in this figure here. So here you can see we have a base station, and it transmits or communicates with a number of mobile stations. However, the mobile stations that are marked here in with red circles, they are hidden from the base station, so they do not have a line of sight connection. And as such, the quality of service they can receive is relatively poor, especially in modern systems that move to higher and higher frequencies. And at those frequencies, if you do not have a line of sight, then the connection will be poor. And there's not really much you can do at the transmitter and at the receiver to overcome this, right? Because if you increase the transmit power, this comes with a whole host of other challenges, right? So this is not really a good option. So therefore, with the current state of the art, those users just have to live with a poor reception. Likewise, secrecy and security become more and more important in wireless communications. And there, the challenge is that if an eavesdropper has basically a better channel than the legitimate user, as is the case here in the scenario that I depicted here, the secrecy capacity will be essentially zero, right? So there's not much you can do in this case either, and you just have to live with an insecure link or not transmit at all. Now, these sort of somewhat naive considerations, they somehow motivate us to try to not only tackle transmitter and receiver, but extend our design space also to the channel. So the idea is to convert this God-given wireless channel into a programmable smart radio environment. Now, of course, the question is, how can we do this, right? So how can we make the channel smart? And the answer to this is probably the use of intelligent reflecting surfaces. Now, what are these surfaces? So these surfaces at RF frequencies are essentially arrays of, either metamaterials, right? So that can change the reflection properties in a continuous manner across the surface, or maybe more realizable in the near term, simply patch antennas, so discrete patch antennas, as sort of indicated here on this surface, that have a size on the order of maybe half a wavelength and are connected to phase shifters. And these phase shifters can manipulate the phase of the incoming wave. Now, with such surfaces, you can basically change the behavior of the reflected phase, of the reflected wave. And for example, you can realize functionalities such as an anomalous reflection, so where the incident angle is different from the reflected angle. Or you can realize beam splitting, where you split an incoming wave into two waves. Or you can focus an incoming wave or collimate maybe a diverging wave or a diverging beam, and thereby customize your wireless channel, at least to some extent, as we will see, and improve the reception quality at the desired receivers. Now, if we had such surfaces, right, in the channel, then you can see here how they could be exploited. So in the previous scenario that I showed with the blocked mobile, you can see if we can code here the surface of another building with this intelligent reflecting surface, then we could manipulate this incident wave in such a manner that it gets reflected or focused on the mobile here, and thereby significantly improve the channel quality, right? So that's one idea. The other one is with the eavesdropper. You can also see here, we can basically transmit around the eavesdropper and thereby give the desired user a better channel than the eavesdropper, right? And this, of course, would solve our problem with the secrecy. Now, these intelligent reflecting surfaces, right? This sounds very good, but is it also practical? And indeed it is, right? So prototypes have been already developed. So this prototype here that I show here, this was developed in the paper that is referenced below. And this is our first proof of concept. That's not the only one. So there are others, as I will show you in a little bit. But one thing to notice here, that for this surface that was realized, it consists of 100 times 100 such patch antennas with a phase shifter attached to it. It's also sometimes called a unit cell. So it consists of 100 times 100 such unit cells. So in total, there are 10,000 unit cells. And it operates at a frequency of about 10 gigahertz, right? So this has already been shown. Now, as I said, there are other such realizations or implementations that have been proposed. And this I took from a tutorial from Marco Di Renzo, where he collected sort of figures of such implementations together with the institutions that reported them, right? And this was already some time ago. So nowadays they're even more available, right? So, I mean, many companies and universities worldwide, they develop now such surfaces. So this is a technology that is at a very early stage still, but definitely, getting to the stage where prototypes become available and also are being sold. Now, this was the RF part, right? So how would this look like at an optical frequency, right? So you saw before the frequency was around 10 gigahertz. Now we move to much higher frequencies, and we try to see what are the similarities and what are the differences as we move to higher frequencies between these IRSs. And for optical frequencies, there are mainly two sort of types of communication systems that are considered. One is visible light communications. So this is mostly for indoor communication, and you use a conventional lighting system and transmit in addition information. The other version that I will emphasize here is free space optical communication systems. And there you use a laser beam to transmit information from a location A to location B. It's similar to fiber optical communication, except instead of using a fiber as a waveguide, you use the air basically as the waveguide. And you use a focused laser beam to transmit. Now, such systems, they are used, for example, for backhauling in wireless systems or for enterprise networks or campus networks for high rate point-to-point links. Now, the limiting factors, of course, there are a few limiting factors of such systems. So one is simply the turbulence in the air. So it's like a fading effect, similar to fading at RF frequencies. Then the laser beam will diverge over distance, and this causes a loss of power at the receiver. There might be misalignment errors. So this means that you have to align the transmitting laser to the receiving lens at the receiver. And things like building sway, right, or wind gusts, they can cause a movement of the building and then cause misalignment between the laser beam and the detector, and this will also lead to fading and may even lead to outages. Now, finally, quite obviously maybe, you need a line of sight link between transmitter and receiver, right? So the laser beam, unless you have a line of sight between transmitter and receiver, this is not going to work. Now, for most of these limiting factors, countermeasures have been proposed over the years, right? So there's also a MIMO FSO, there are hybrid RF FSO systems, and relays have been proposed. So here we propose sort of a new concept, and that is to avoid this line of sight or to circumvent this line of sight requirement by using optical intelligent reflecting surfaces. Now, what is an optical intelligent reflecting surface? Well, in the optical domain, you have actually more options than in the RF domain, because all of you are already familiar with an optical IRS, right? And this is every morning when you are in the washroom, right, in the bathroom, then you actually look into an optical IRS, and it's just a standard mirror, right? So in the end, the optical IRS, at least one type, can be a standard mirror that reflects your incident laser beam. Another more sophisticated option are micro mirrors, and I will discuss those two in a little bit. But of course, people have also proposed to use a meta-surface-based IRSs at optical frequencies, and those might be non-reconfigurable or reconfigurable. Now let's have a look first at the standard mirrors, right? So a standard mirror, of course, can only realize specular reflection. So if you want to change the direction of your laser beam, you may have to mechanically reorient the mirror, right? So you may have to mechanically tilt it in order to get the desired type of reflection. This technology has a very low functional capability, right? So you cannot focus a beam, you can just reflect it, and it's not that tunable, but it's very cheap and mature. So you can already buy such mirrors today, right? So this is, of course, a big benefit. Then the second option would be micro mirrors. So this is an array similar to an antenna array, but here it's an array of small mirrors, and every individual mirror can only realize a specular reflection. You can reorient them via mechanical tilting, and since you can reorient the different mirrors differently, it's a little bit more tunable compared to the standard mirror. It's also more mature, of course, but you can so you can buy these devices already, but not at the size that we would need for FSO systems. So typically the size of these mirror arrays are quite small, but in principle this technology is available, right? So that's the big benefit. Then for meta surfaces, so those have been proposed in the physics literature mostly, and the non-reconfigurable type is the one where you basically fabricate them once, and then they realize a certain incident and reflected angle, but they're not adjustable afterwards. So they use small nano antennas and that change in geometry in order to realize a phase shift. They have a better control resolution compared to mirror. They have high functional capabilities, but they're not tunable, right? The non-reconfigurable ones. And it's proof of concept. So mostly this is still in the physics literature. So there's not something that you can go and buy today from a company. Then the final option would be the reconfigurable meta surfaces. So those have tunability, and basically you change certain material properties electrically, and thereby you can change the phase shift across these surfaces. And there are different options for this. So you can change the charge density, for example, or the structure, right? Or the molecular alignment, for example, in liquid crystal based surfaces. They have a good control resolution, high functional capability, high tunability, but very much at the proof of concept stage. And again, not something you can buy in a store, right? So this is also something that still needs development and, you know, may become mature in the next, I don't know, 5 or 10 years or so, depending on demand, I guess, as well. Now, what has all of this to do with wireless communications, right? You may ask, these surfaces. So let's look at the long-term vision here. So it's always good to look in the past, right, and how things have changed, right? So now, today, these intelligent reflecting surfaces, they may sound quite futuristic and fancy, but 40 years ago, right, or I guess 50 years ago, this is what a mobile phone looked like, right? So this was a mobile phone 50 years ago. And since then, of course, we have come a long way, right? So wireless technology has changed significantly and is much more sophisticated today. And therefore, the vision for the future is basically to not limit our design to the transmitter and the receiver, but also incorporate the channel and create sort of a wireless 2.0, where we can design the channel such that it best serves the current communication needs that the users have in the environment, right? And for this, you would have to make the channel programmable. And the idea is to do this via these, you know, reflecting surfaces whose properties can be adjusted. Now, before this is possible, right, so many research problems have to be tackled. So the first problem sort of is the modeling of these systems, right? So we need physics-based models for these surfaces in order to fully reflect their actual capabilities. Then based on these models, we have to design the wireless system, including the IRS, right? And see what gains we can get and develop corresponding algorithms. A big issue that I, you know, sort of pull out here is the acquisition of the channel state information, right? So you saw before that we had an IRS with 10,000 elements. Now, if you want to estimate the channel to each individual patch antenna, this may not be very scalable, right? I mean, this is not possible. So there's still a need to develop intelligent CSI acquisition mechanisms. Then once this is settled, of course, we will have many IRSs in the environment. So we have to orchestrate them and develop a networking theory and technology for IRSs and of course also the other components of the network architecture. Then there are many, I think, interesting information theoretical questions here, because if you look at information theory, usually you know, the channel is the part of the system that you cannot modify, right? So that is fixed, and then you calculate the capacity, for example, of that channel. Now this will change, right? Because we have an adaptive environment and we have a channel that we can manipulate. So maybe we should rethink some of these basic concepts in information theory as well. Then, of course, implementation, right? So I showed you some proof of concept implementations before, but those are still very bulky and, you know, just that proof of concept. So I think a lot more work in sort of this domain of electronics and microwave engineering will be needed. And then in the end, of course, we have to combine this with appropriate applications and see how they can benefit from this. Now, in this talk, I will focus on the first two aspects, so on the physics-based modeling and on the design of such systems. But even then, this is a multifaceted problem, right? Where you have to combine sort of knowledge from electromagnetism, communications, and signal processing. So the models, they require knowledge in electromagnetics, right? So to come up with physics-based models, not just with, you know, made-up models. And then we have to cast these models into a form that is suitable for communication theoretic analysis and design. And then, of course, develop low complexity algorithms for their operations. So this is sort of the broad introduction that I wanted to give. Now let's become a little bit more concrete and have a look at the modeling of such surfaces at RF frequencies. And here I want to make again the point that these surfaces in reality, they will be large, right? So they will have 100 times hundreds unit cells, right? So 10,000 unit cells or more. And to understand why that's the case, we can look at the theory, right? So basically in this slide, I summarize one of our results where the question that we asked was the following. So we said, okay, the IRS, the purpose is to replace a direct link, right, between the transmitter and the receiver. And then one legitimate question is, how many of these unit cell elements do I need, right? So how many phase shifters do I need for this virtual link, right? So this reflected link to have the same strength as the direct link that I want to replace, right? So I want to make those two equal. And then with some math, you come up with this lemma here and this equation for the number of unit cells elements you need. And you see this is related, of course, to the distances between transmitter and IRS, receiver and IRS, the distance of the direct link, the size of these unit cells, right, of your patch antennas, and the wavelength. And then if you plug in some reasonable numbers, right, so say about here 100 meters, 200 meters for these different links, and your operating frequency is 5 or 10 gigahertz, then the result that you get is that you need 3,000 or 6,000 of these unit cells in order to replace a direct link, right? So you need a very large number of these unit cells in order to get a meaningful performance. And this is still optimistic because we did not take into account many losses for this IRS that you will have in a real system, right? So this is still actually an optimistic result. And this shows that if these systems are to be realized, right, you need to do something to make it scalable, right? So many of the early papers, and not just also my own early papers, right, we assumed a very small number of unit cells, right, on the order of 100 or so, because the algorithms that we developed, they could not deal with larger number of unit cells. And the only reason we got again, and not just us, also others, was because we made very pessimistic assumptions about the blocked link, right? So we assumed that the link is blocked. And of course, if you compare a fully blocked link with a very weak link, the weak link is still very good. And maybe also sometimes the channel model, was not 100% realistic because the modeling was not that sophisticated. So therefore, here we advocate a scalable modeling. And one step to this that we advocate is to divide the entire IRS into so-called tiles. So those are smaller subsurfaces. And I will go more into details about this when I talk about optimization. But this motivates us here to basically model the impact that one of these tiles has on the incoming and reflected wave. For the surface, we assume that it's either continuous or discrete, right? So continuous would mean that we have a metamaterial, and discrete would mean we have patch antennas. We will consider both cases, but we start with the continuous case, and we model the impact of one tile. Now, for the incoming wave, we assume that it's a plane wave, right? So characterized by its electric and magnetic fields, basically. And it can have an arbitrary polarization. The reflected wave is also characterized by the corresponding fields and can have also an arbitrary angle, or we can observe it under an arbitrary angle, right? So this is just to sort of clarify what our assumptions here are. The surface we model basically by a reflection coefficient that includes a constant amplitude, and this amplitude we assume is fixed, so it's independent of the x and y directions, which of course is a approximation, and it can be chosen such to basically model losses and the passiveness of this IRS. what we design is the phase shift, and the phase shift across the IRS depends on X and Y, right? So this is the degree of freedom that we will optimize or that we can optimize in such a system. And here we assume that it's continuous, so it can be changed at any position in any desired manner. Then for the analysis framework, we use basically Maxwell's equations and try to find a relationship between the electric field of the reflected wave and the electric field of the incoming wave. And yeah, I don't, you know, this is in the paper, so I don't want to go too much into detail, but essentially it does not go beyond this book by Balanis, right? So there's this book by Balanis on advanced engineering electromagnetics. And essentially what you need does not go beyond the knowledge in this book, right? So it's just an application of what you find there. So then the IRS itself, we characterize then with a so-called generalized radar cross-section, which is the ratio of the electric field of the reflected wave and the electric field of the incoming wave, both under certain angles that can be freely chosen, right? So this psi r and psi t, those collect the elevation and azimuth angles of these two waves, and they can be chosen arbitrarily. The front part here, this is just a normalization term that makes sure that this radar cross-section does not vanish, right? So as you observe it at a large distance, because we assume that we operate in the far field here. Now, this basically captures the amplitude and the phase of the reflected wave, right? So in the end, it's sort of the characteristic or the beam pattern that an IRS will cause for an incoming plane wave, right? So this is what this generalized radar cross-section will deliver. We call it generalized because we are also interested in the phase, whereas usually in the radar literature, when they talk about radar cross-section, they're only interested in the amplitude. Now, this generalized radar cross-section can be calculated for such a IRS or for such a tile. If you fix the phase shift function, right? So the phase shift across this IRS. And here we assume that we have a linear phase shift in X and Y direction, right? So this beta X and beta Y are the linear phase shifts in X and Y direction. And linear means that essentially you optimize your IRS for an incoming wave coming from direction psi t star, and an outgoing wave going into direction psi r star, right? And both are modeled as plane waves, right? And in addition, you can have an offset here, this beta 0. So this is a general phase offset for the entire tile, right? And if you plug this into the equation that I showed before, then you get this equation here for this generalized radar cross-section, or you can also say for the beam pattern of the IRS. And I will show you this in a little bit, what this looks like. But first, I just want to make the point, this is for continuous tiles, right, or continuous IRS. You can do the same for the discrete case. You get a very similar formula, just the sinc function gets replaced by a sine by sine function, right? So this works exactly in the same manner. And I will illustrate this here with this example. So here in this example, what we see is this generalized radar cross-section, or beam pattern, if you want, of the tile, where our IRS was designed as follows. So we chose for the desired incoming angle, we chose this to be perpendicular to the IRS, right? So that's the incident wave. And the outgoing wave has an elevation angle, sorry, an azimuth angle of 30 degrees and an elevation angle of 45 degrees. So this is how the IRS is designed. Now the actual wave that hits the IRS, fortunately, comes from the same direction for which the IRS was designed. So it's also perpendicular. And we observe the reflected electric field also under the same elevation angle, so under these 45 degrees, but we vary the azimuth angle. So the azimuth angle, the designed azimuth angle is 30 degrees, but we show what we observe, what field strength we observe in different directions, right? So basically we collect the beam pattern. And you can see that the maximum of this reflected wave is at 30 degrees, as we would expect, since that was what we designed it for. But of course, you do not get just a contribution for 30 degrees. You really get a beam and with side lobes because of the finite dimension of the IRS, right? Because it has a finite size. And this is for the continuous case. Now, if you replace this with a discrete IRS and you choose the same parameters, you get the blue curve. And you can see this looks very much the same, right? So there's not much difference. And here the discrete IRS uses patch antennas of size of λ/4, right? So a quarter of a wavelength. And if we change this to half a wavelength, then we get the red curve. So you see the deviation is a little bit larger, but still, quite small. Then for the discrete IRS, usually you need to leave some space between the different patch antennas. So if you leave some space, you get a little bit of loss because you lose power. That's why the green curve is a little bit lower. Then if you quantize your phase shifters to 3-bit, you get the yellow curve. And again, in the main lobe, you have hardly any loss. In the side lobe, you have a small deviation. If you further quantize to 2-bit, then you get this, magenta dashed line, so a little bit more deviation. And if you quantize to 1-bit, then the deviation becomes a bit larger, but still you have the same main characteristic of your beam, right? So you still have a main lobe, and then you have some side lobes. So you can see these discrete IRSs, they approximate, even with quantized phase shifts, they approximate the continuous IRS quite well. Okay, so this was for the RF modeling, right? So how we model the IRS there. So let's move to the optical case, right? So what is different there, and how can we model the IRSs in the optical domain, right? And this is a situation we look at. So we have a laser source, it hits the surface, and then we have a optical lens that we observe. And this picture you can keep in mind throughout this part of the talk, the setup that we will consider. Now, what is different as we move to higher frequency, right? So what changes for our system, right, in terms of the modeling and the mathematics as we go from, RF frequencies to higher frequencies? And we will look here at basically 3 aspects. So the first is the electrical size of the IRS changes. The second is the analysis methods change, and actually they become much simpler. So you can use simpler tools. And then also there's a difference between the type of incident waves that we have to consider. Let's start with the electrical size. So the electrical size of the IRS is defined as the size of the IRS, the physical size, divided by the wavelength. And if we compare this for a physical size of the IRS of 10 centimeter, and we consider the electrical size for a gigahertz system, so 3 gigahertz system, a 30 gigahertz system, so millimeter wave, a terahertz system, and optical system, then we see that the electrical size changes tremendously from 1 to 10 to 1,000 to 100,000, right? So at optical frequencies, the same IRS of the same size, no, not the same IRS, but the IRS of the same size, changes its properties significantly because it is electrically much larger. What does this mean? This means that at optical frequencies, we have a higher flexibility in terms of beam shaping, right, with the same size IRS. And the analysis techniques that we can use, they become simpler because we can use geometric optics instead of a wave-based analysis, as we will see. Now, this is illustrated also in this figure. So this is sort of the setup that you saw in the first figure, right? With the laser source, the IRS, and the photo detector or the detector plane. And here we show the power density of the reflected wave close to the receiver. And it's always the same IRS, but for different frequencies, right? And the blue curve is for a millimeter wave frequency. And you can see the shape is very much the same as what we saw before when we analyzed RF IRSs. Now, as we move to terahertz, you can see that the IRS becomes much more selective, and basically the side lobes they become smaller. At optical frequencies, this is the red curve here, you can see that we have a very narrow beam, hardly any side lobes, and we could get a similar result as the red curve actually if we just use geometric optics, where we would not use a wave-based model, but we would just model the wave as a ray, right, that connects 2 points. This is the gray curve, the gray rectangle here. We would get with geometric optics point of view, which is much simpler, but yields quite good results at these optical frequencies, right? So that's a first hint that, okay, as you go to higher frequencies, things change. Then the incident waves that we have are different. So for RF, we have a plane wave or a spherical wave, depending on whether we are in the far field or in the near field. For free space optics, typically we have a very concentrated waves that's modeled as a Gaussian beam, right? So mathematically, this is written here. So this would be the electric field. It's not so instructive, but here in this figure maybe is clearer. So here you have the intensity in X and Y direction, right? So the laser beam basically has the highest intensity in the middle. You see this also here. So this is if you look at an area that is hit by the laser beam perpendicularly, right? So then here in the middle, the intensity of the laser beam is the highest, and then it decreases sort of in a Gaussian manner as you move outside, right? So here outside, you have hardly any intensity of the laser beam, right? So any laser power, and in the middle, it's the highest, right? And this has, of course, also consequences for our modeling and for how the IRS affects the laser beam. Now, the receiver here is typically a lens, right? So here the gray part is the lens, and the brown part is the laser beam that hits the lens. And the performance measure is usually how much power you can collect, right? Since usually for these optical frequencies, at least for these free space optic systems, intensity modulation is used, where the intensity is used to carry the information, not necessarily the phase, right? Now, for the analysis methods, we have several options, basically. So we can use either wave-based models, and this would be via scattering theory or Huygens-Fresnel principle. And those two are similar to what we've seen before for the RF case, right? So they give you similar or the same results. However, the simpler model would be actually a geometric optics-based model. Now, for scattering theory, you basically model your IRS as a surface with discrete reflection points, right? So maybe patch antennas. And then each reflected point is then modeled as the origin of a spherical wave. And, where you observe the wave, you just add up all these spherical waves, potentially with a phase shift superimposed, right, due to the IRS. And then you get this expression, which is not very nice, but you can easily calculate it or evaluate it with MATLAB. Huygens-Fresnel principle is very much the same, right? So also a wave-based model, and here just the surface is continuous, so you get an integral instead of a sum. Now, the one that we advocate is geometric optics for optical frequencies. And here the question is, when can I approximate a wave propagation with a ray tracing model? Now, ideally, we would need the wave to be very narrow, right? So we have zero beam width in order to approximate it by a ray. In reality, of course, you could do this approximately if the beam width is smaller than the largest dimension of interest that you have, right? And since the beam width is inversely proportional to the electric dimension of the AM radiator, so in our case, the IRS, therefore we can make the beam width quite small because our IRS is electrically large. And therefore we can actually use this geometric optics usually for optical frequencies. And the benefit is that now a point in space only receives power from a ray if it's along the propagation line, right? So there's only a reflection, there's no diffraction. And we can use, for example, image theory to simplify things as we did. So again, the model here, looks a bit similar if you don't look carefully to what we had before. but if you actually evaluate, it's much simpler than the wave-based model. And to show this, I show you here one result. So again, we observe the received power density in the plane in which the receiving lens is located. And we have an IRS of size, I guess, 10 or 10 centimeter that reflects the incoming beam, right? The incoming laser beam. And if we analyze this with geometric optics, you get this result here for the power density. So you can see here on the shape, that's the Gaussian shape, right? So as you go further away from the center, you have a decrease in the intensity. That's a logarithmic scale here. And then here it's cut off because a part of the laser beam is just outside your IRS. Now, if we analyze the same system, not with geometric optics, but with this Huygens-Fresnel principle, then we get this result here, right? So the blue result. And you can see that, okay, there's some diffraction also in this case, right, at the corner points. If you use the other model with the discrete patch antennas, you get the red curve. And if in addition you do phase shift quantization, you get the green curve. Now you get some deviation here, but if usually you're interested, on the part where your photodetector is located, right, your receiving lens, and that's the blue part here. And you can see for this blue region, there's hardly any difference between the received power that you would predict with these different models. And therefore here you could really use this geometric optics and you would predict the actual behavior of the system very accurately. Now, to look at the time. Now, in the last part that I want to look here at the modeling, we want to have a look at the impact of the size of the IRS, right? So I mentioned before that the size of the IRS has a large impact on, the electrical size of the IRS has a large impact on what happens to our reflected wave. So basically, we will investigate this here in the next figure. And besides, we also want to basically answer the question, what is the difference between pure reflection and focusing, right? I mean, can we get a gain if we do focusing instead of just reflection? Under what conditions do we get a gain? And when does this geometric optics-based analysis become accurate? Now, all these questions are answered in this figure, so I will need a little bit to explain it. So it's the same setup still as in the beginning. So we have a laser source, an IRS, and a receiving lens. And what we observe here, what we show here, is the power that the receiving lens collects, right, at the receiver, as a function of the size of the IRS, right? So here we increase the size of the IRS from 0.1 millimeters up to 1 meter, right? A square or a square area. And we have a number of curves here. Let's start with this blue curve. The blue curve is if we use a mirror for the reflection, right? So we have a simple mirror and we reflect this laser beam with a mirror and we collect the power at the receiving lens. Now, what do we see? Well, first, in the first regime here, so for very small IRS sizes, you can see that the received power grows basically as n square, where n would be the number of unit cells that the IRS has, right? So it grows with the square of the size of the IRS. And this n square growth, this is a very well-known result from the RF literature, right? So for RF IRSs, it has been shown that the received power or the SNR at the receiver grows as n square. And where does this come from? Well, here in the optical domain, this n square growth has two reasons. So first of all, as you increase the size of the IRS, of course, you collect more power from your laser beam, right, from your incoming wave, and this contributes a linear growth. And then as your IRS grows, you can also do a better job in beam forming your signal to the receiving lens, and this is another growth, another linear growth. So both together give this n square growth, right? And therefore, this is what we have. And this is the only growth that sort of is known from the RF literature, right? Because with plane waves, you always get this sort of behavior. Now, as the IRS grows further in the optical domain, right, eventually your IRS will be able to focus or to forward all the energy it receives to the receiving lens, and you don't get any additional gain from the growth of the IRS in that sense. The only additional growth you will get is because the IRS itself collects more energy. And therefore, the scaling law changes from square to just a linear growth with the size, right? So this is this domain here. And then eventually, your IRS is so large that it collects all the energy that the laser beam has, right? Because it covers the entire laser beam. And then you saturate, right? So you don't get any additional gain. So therefore, you can see here the behavior is very different from the RF case here in the optical domain. So that's the first point that I would like to make. Then if we would use, instead of this mirror, a focusing meta surface, then we get the red curve, right? So this is the red curve here. And you can see for small sizes, actually, we get a slightly worse performance than with the mirror. And this is because the mirror is tilted and therefore sort of has better reflection properties compared to the flat surface that may have a bad incident angle or a bad reflected angle, and therefore loses power here. But eventually, as the surface becomes electrically large, right, then of course the focusing will improve performance and you outperform the mirror, right? So for larger sizes, the focusing is actually beneficial. Now, the red and the blue curve, those were obtained with scattering theory, right? So those are accurate results regardless of the size of the IRS. The other two curves that you see here are for the same type of surface, but those are not for scattering, but theory. They are for the geometric optics point of view. And you can see that for small sizes of IRSs, geometric optics is very much off, right? So it doesn't give you accurate results. But for larger sizes, it becomes very accurate and coincides with the scattering theory, as we would expect, right? You can also see that the size actually that we have here of the iris is not that large, right? So here we are just at 10 centimeters, right? And at 10 centimeters, this geometric optics view becomes already accurate. And also you get high performance. So therefore, in reality, for practical cases, for optical IRSs, geometric optics will probably always do. Okay, so now I think unfortunately I already run out of time and I still have two chapters to go. So therefore, I think I will just give you an idea of what is in those two chapters and then without going into details. So this one here, the second one is the design of the IRSs. And here the idea that we want to propose here is to divide the IRS into tiles. And then for each tile, we design a number of beams, right, that point in different directions. And then in the end, in the optimization phase, in the online optimization, what you do is you just select one of these beams for each tile, right? And then you optimize this together, for example, with the beamformer at the receiver. The benefit of this is that you do not really have to optimize each individual phase shift, right? So you don't have to optimize 10,000 phase shifts. What you have to optimize is maybe a number of beams, right? So maybe 50 or 60 of these beams, and you have to select one of them. So with this, you can make both the channel estimation and the optimization much more scalable, right? And there's a paper on this, so you can find the results there. So this is the basic idea. For the optical case, basically it's similar. So here, a major impairment for free space optical signal systems is a building sway, right? And the misalignment error that this causes. And this is one of the aspects that we analyzed here, right? So traditionally, you have this building sway only at the transmitter and the receiver, and this causes misalignment. But if you have, of course, an IRS, then you may have additional impairment at the building at which you basically place your IRS, and this will also contribute to the degradation. But we could show that this is still manageable, and you still get a significant performance gain compared to not having this, right? Obviously, because you circumvent the line of sight. Yeah. Okay, so as I said, I mean, I'm happy to make these slides available, and then if you're interested, you can have a look afterwards. So just let me summarize a little bit and give some ideas for future work. So these IRSs, the main idea is really to customize the wireless channel, right? So to adjust it to the needs of a communication system. The idea that I want to convey here is that how we design these IRSs and the concepts that should be used for their design, they are very much dependent on the operating frequency, right? So that's an important aspect. And it's important to have a physics-based model, right? Not to just propose a model that seems to work, but one that really you can sort of tie back to the actual dimensions of the IRS and the actual powers that you would observe. So if it's based on physics. And the model that we propose is valid for arbitrary incident, reflection, polarization angles. It depends on the different physical parameters. And what we showed, and which is sort of consistent with people that do experiments, is that you need a very large number of these elements in order to get a significant or a noticeable gain even. Then for the scalable design, we propose a two-stage approach, right? So one is the design of these beams, right? Codebook design, we call this, and then the selection of the best mode for each of the tiles. And this gives you sort of a scalable and tunable complexity performance trade-off. Now, for future works, I mean, there are, of course, many people work on these issues already, of course, but I think for the modeling, this is still important, right? The physics-based modeling, and to make these models more realistic, but still sort of manageable. So one is to include also the losses of circuits, right? I mean, that you have there, right? We assumed that the amplitude is constant over the entire surface and independent of the phase shift. You know, that's in reality not really the case. Also, active IRS have been proposed, right, in order to deal with this, you know, in order to mitigate the large number of elements you need. If you make your IRS active, then you can do with fewer elements, right? So, but for this also physical models are needed. And then for the optical IRS is the same, right? So we only have modeled so far the mirror and some very, you know, specialized meta surfaces. But for the other types of optical IRSs that I've mentioned, also it would be interesting to develop models. Then for this two-stage design approach that I didn't explain in so much detail, but we only have looked at this for very simple network architectures. So this would be interesting to generalize. Then you can solve this either by optimization, and there's room for improvement in terms of the algorithms that are used, or maybe using machine learning tools, right? That might be a good fit in this case. This would be also an interesting direction. And then, of course, the code books that we propose, they could be improved. Other directions is the channel estimation, right? So really channel estimation is a main bottleneck for these systems, right? Learning the channel. And you know, this is still largely open, I think, to come up with you know, scalable and high performance frameworks for channel estimation. And then, you know, most people look at these IRSs just as a way of you know, overcoming situations where the main link is abstracted. But maybe there are also ways how they can improve a link if you do have a direct link, right? Maybe by increasing the multiplexing gain that you can get in a system, things like this. And I think this should be also more investigated. And finally, information theoretical analysis would be interesting. I mean, there are some works now that you can find in the literature, but there's still a lot of, you know, a lot of work to be done. Okay, so sorry for taking so long and still only getting to 2 chapters. So thanks a lot for your attention. And now I'm happy to answer your questions.
Thank you, Robert, for your very nice talk. So now you move to the Q&A section. So feel free, everybody, to write your question in the chat box. We have some questions from the participants. So let me check. Okay, one question is about the effect of mutual coupling between the IRS elements. So what, how the mutual coupling would affect the activable channel capacity, and how we can model?
Yeah, so I think people have modeled this by introducing sort of a correlation matrix. You know, that would be one way, and yeah, I guess it would degrade performance, right, compared to what we can achieve without this mutual coupling. But I'm not sure that it will have such a large impact, because first, I'm not sure how strong it will be, because the power that we receive at the IRS is low anyways, right? So it's not like at a transmit antenna where we transmit a very high power, right? So the power that we reflect is very low, and therefore maybe the mutual coupling is not that severe, right? But I think that's one of the things that, okay, we need to get more accurate models, right? That's one thing. And the other thing is also, I mean, and some people have proposed models, right? But I also think, you know, there really we need to do experiments, right? So I think this will be difficult to find out the full truth just by analysis, right? So probably we need experiments and see how large or how much of a problem this really is. Yeah.
Okay, another question is about the application in vehicular domain. So do you think this can be applicable to vehicular domain for multi-user communications?
By using, so this was for the optical part, I think, because it
Yes.
says by using the head and tail light.
Yeah.
Yeah, that, well, this is then more in the direction of, I think, visible light communications rather than free space optics, right? So free space optics usually assumes a laser beam, and transmitter and receiver are very much aligned, right? And people have proposed to use this in a sort of vehicular environment, for example, for high-speed trains, right? So where you exactly know which way the train goes, and you have your laser and that tracks the train, right? So I think that, you know, to get a high rate link, that would be possible. For vehicles, yeah, I mean, I'm not sure how adaptive we can make the, you know, how fast the laser can adjust to unpredictable movement, basically. But I mean, in terms of visible light communications, yes, I think that would be possible, right? But then the rates would be probably lower than what you can achieve with, compared to what you can achieve with free space optics and the laser.
Okay, another question is what's the difference between IRS and ambient backscatter communications? Can IRS send information?
Well, I think, you know, it's a broad, you know, IRS has been used, you know, the definition is very broad, right? So different people use different definitions of it, right? So yes, so some people have, I mean, for me, in the context of this talk, the IRS basically just, you know, is sort of a reflector for an incoming wave, right? So it cannot, it does not send information of its own. But of course, there are also proposals where IRS sent their own information, right? So and similar to, a little bit similar to backscatter communication, and also are just modulated by an external power source, right? And then sent their own information. So I think, you know, the transitions are somewhat fluent, right? But the original idea of IRS was that it's a reflector, right? So it would be different from backscatter communication.
Yes. Okay, I have one question. It's about the research challenges that you mentioned. There are many indeed. I think another one would be to establish the initial link when you consider in IRS assisted optical system, right? Because even for a point-to-point free space optical system, this is very, I mean, challenging. And if you want to initialize, for example, the IRS to detect the received power, I mean, for example, if you use a phase shift configuration, it's not guaranteed that you are going to detect, even because you need a desirable narrow beam, right?
Yeah.
I mean, so how can we address this issue in IRS assisted optical system? I mean, this establishment of the initial link to start the connection.
Yeah, I see what you're saying. Yeah, so basically, right, how do we figure out that, okay, they are,
Yes.
you know, that the IRS should point in this direction? Yeah, so I think I've not seen any research on this, right? So I don't know, I'm not sure, I don't think anybody has really addressed this. Of course, you could have sort of a, you know, a low rate RF system that helps you with it, right? So that tells you what the coordinates of your receiver is and so on. Also, I mean, usually these, I mean, at least in the non-mobile case, right? I mean, which I think is the bulk of the applications, you have to do this once and then you're done, right? So, I mean, maybe you have to basically track a little bit the building sway and so on, right? So you need maybe some tracking capability, but to get the initial, to get the beam, you have to do this once, and maybe then you have time to do this, right? So it's not that you can do it by trial and error, right? I mean, to establish the first link if it's just a fixed receiver. But I think this might be an interesting topic as well, right? I mean, you could think of something like having a hierarchical design, right? So where first you use a broader beam, right, and then you are more likely to detect something, and then narrowing it down slowly, right? So I think there are different options that one could come up with, probably.
Maybe we can start by generate a wider beam, right? And after the connection is established, you can make some refinements to adjust the phase shift of the RRS. Yes.
Yeah. And the beam, as at the IRS via the phase shift, right? You can also adjust the beam, right? So both here at the laser source, but even here, right? How you reflect the beam, right? You can sort of make it wider or narrower, right? So yeah.
Okay, thank you. Another question is about okay, when compared to microwave and to optics, what do you say about the terahertz region? Is a constructive interference of benefits or of drawbacks for IRS approach? I mean, compared to microwave and optics, how about the terahertz region? It should be constructive.
I don't understand the constructive interference, right?
That's
yeah, so I think that the terahertz, many people are excited now about this terahertz, right? And I think, I mean, what I see is that, okay, you have a very large bandwidth, right? So that, I guess, is the obvious thing. What I think is actually difficult is getting a very wide range, right? I mean, transmitting over long distance. At least that's, I mean, I talked to some, I mean, I'm not in hardware, right? So I have to rely on what other people tell me. But what they say is that actually, it will be difficult to transmit over longer distances because you would need very high, relatively high transmit powers, right? So it's very difficult to build efficient transmitters that allow you to transmit over, say more than a few meters, right? And a few meters, we talk about maybe, 2 to 5 meters or so, right? And still have a significant received power. So I think it's one of the 6G topics, right? So of course it's exciting to investigate, and also because you also have the line of sight issue, right? Similar to optical frequencies, sort of it's a natural match to combine it with IRS, but how practical it will be in the near term, I'm not sure.
Okay, we have other questions in the another chat box. Let me check. One, okay, it's about the slide number 7. So it's slide number 7, and the question is, for the result on minimum number of unit cells, is the target to get the same SNR as the receiver, as the direct link? It is always necessary. I mean, the reflected link could be an additional source of diversity in our array gain.
Yes, of course. I mean, that's, that's of course not always necessary, right? I mean, so this was just sort of just to give an impression, right? I mean, of the relative strength, right? Because, to get the same strength, you need many, many elements, right? If you're, of course, fine with 1/100th of the strength, right? Then it's enough if you have 1/100th of the unit cells, right? But this is still, of course, that's true, right? I mean, but usually it's sort of sold as a replacement of the direct link, right? And if you want to use it as a replacement of the direct link, then you will need many, many unit cells, as is also basically seen by these practical systems that have been built, right? So I think, of course, it's interesting to look for use cases where you need fewer links, right? So this would make it much more practical maybe in the near term, right? I mean, if you can find a scenario where you can get a significant gain just with 100 unit cells or so, right? Then, this would make it more attractive actually for practical realization, right?
Okay, another question is about slide 13. So what is the motivation for choosing a linear phase shift function?
Yeah, so the motivation, yeah.
Yes.
So the motivation for this is that you would get sort of this anomalous reflection, right? So I think I had this before. Right, so if this is your goal, roughly speaking, right, so that you have an incoming wave under a certain incident angle and you want to create a reflected wave under different angle, then you need this linear phase shift, right? And of course, this is only, 100% valid, this view, if you can replace your wave with a ray, right? So this ray view. But as you could see, approximately the same happens if you have a finite dimensional IRS and you have sort of a wave-based propagation, right? So that's the motivation. So this is sort of, you can say that's arbitrary. And also in the other part that I didn't show you, right? So just let me quickly. So if you use this linear phase shifts, right, and you use different incident and reflected angles, then you get these beams here, right? So each color here is a different beam that you get for different linear phase shift. If you replace this linear phase shift with a quadratic phase shift, right, then you get this sort of beam, right? So then you get this sort of reflected, characteristic. And you can see that with a linear phase shift, you get a narrower beam, right? A narrower main lobe, but then you need more of those narrow beams in order to cover the entire space. In contrast, if you use this quadratic phase shift, your beam becomes broader, the main lobe is lower, so your SNR will be lower, right? But you need fewer beams in order to cover the entire space, right? If you want to select, different beams to serve different users, basically.
Okay.
Yeah.
Another question is, do you think IRS can be used for inter-satellite links of low-orbit satellites or CubeSats?
So for inter-satellite links, basically to reach the other side of the Earth, is that maybe the idea? So yeah, I mean, I've seen that people proposed it for satellite links, mostly for basically the, reflecting the ground link, reflecting the uplink to another ground link. But yeah, I think in theory, whether it's practical, that's I think a different story, right? But in theory, this could be used, right? I mean, but then also I think
how feasible, right?
Yeah, but then maybe also more on the optical side, right? Because actually in these satellite systems for inter-satellite links, they often use optical beams, right? So then actually this free space optics option might be, this might be an option, right?
Yes, yes. Another question is, please highlight the difference between IRS and optical relays.
Yes, so that's also a good question, right? So both exist, right? So right, so here we could, instead of having this IRS, we could have an optical relay. And I mean, the difference in terms of hardware, is similar as in the RF case. So for the optical case, the IRS could be just a mirror, right? I mean, in the simplest case, and so much cheaper. But for the relay, of course, you would need a receiving unit, an amplifier at least, and a transmission unit, right? So it's more expensive. Of course, in terms of performance, the behavior is a bit different, right? Because for the one impairment that you have in these free space optical systems is the atmospheric turbulence. So this is like fading, but it turns out that this fading is distance dependent, right? So basically, the longer the distance, the more severe this fading becomes. Now, if you use an optical relay, you cut this link basically in two parts, right? Because you receive here and you retransmit. So therefore, this helps you with the atmospheric turbulence, right? So the fading gets reduced in some sense. And with the IRS, this is less so, right? Because the IRS just reflects the signal, and therefore you sort of accumulate the fading. And therefore here the relay would have an additional gain that the IRS will not have, right? But of course, equipment-wise, the relay is much more expensive, right? So that's the trade-off that you have. Yeah.
There is another question, very, I mean, closer to this one. It's
Yes.
about, do you think IRS would replace optical relays?
Yeah, that is a good question, but that
Yeah.
I cannot answer. I don't know how how popular actually optical relays are, right? I
Yes,
mean, in real deployment, right?
yes, yes,
I think for sure. I mean, these areas are much simpler, right? So I mean, in terms of, and if it's just a mirror, right, really, that you deploy once and then you connect basically two buildings, okay, you have to clean it once in a while, I guess, in order to still get a signal. But yeah, from that point of view, I think it's much
yeah,
better. I mean, I mentioned before that there are also visible light communications, right? And for visible light communications, also people have proposed to use IRS, right? So there's several groups that work on this as well. Not my group,
yes,
but other groups, they propose this.
yeah.
Yeah.
Okay, another question. Actually, you have many questions.
Yeah, I'm
Uh,
happy. I mean, it's good to have
yeah,
questions, right? So
sorry.
I'm happy to answer them. Yeah, yeah.
Yeah,
No,
we
no, I
are in
mean,
extended the seminar, but
yeah, I have time. No worries. Yeah, yeah. I'm happy to
thank
answer.
you. So how about another question is, do you think this optical IRS would replace the classic adaptive optics in telescopes?
I don't think they would really probably replace it, but that could be combined, right? So I think I mean, this adaptive optics usually you use at the transmitter and the receiver. And here in our IRS, of course, there could be some adaptability, right? If you have these metal surfaces, right? These metal surfaces, they could also basically help you focus the beam, right? And one of the things we actually could show was that in one of our papers is that if you have an IRS, right, actually you can get a better SNR than if you had a direct link here, right? And the reason is because the IRS can refocus the beam, right? So the red beam basically will diverge, right? But then the IRS can refocus it. So in the end, you get a better SNR than if you had a direct link that had the length of the two links together, right? But as I said, in the part about the feasibility, right? These optical IRSs that are adaptive and even the non-adaptive ones, they are at a proof of concept stage, right? So if you look at these papers that propose them, they're very small in size, right? So they have a few millimeter in size, basically, what they show. And they're not, it's not something you can buy today, right? So they're not technologically mature yet, but maybe in the future, this could, could become mature and then at least help in this regard, right? I'm not sure if it's, I don't want to speculate if it would replace it, probably not, but
Yeah.
say supplement.
It's a very, very strong, I mean, affirmation, no? To replace something, it's a little bit, I mean, you need to be careful. Think, okay,
Yes, yeah. I think I think some people
yeah,
would not be happy, right, if we would say that this will
yes,
be replaced. Yeah. Yeah.
yeah.
Yeah.
Another question is about what are the constraints that we should consider before incorporating IRS channels in a fog radio access network architecture?
Oh, okay. So that's very specific. So yeah, I
Yeah,
think it's a good question. And yeah, actually, I don't think I have a very good answer for this, right? So I think my main, I mean, regardless of fog radio or not, right? Really, one of my main points is that in reality, if you take into account all the parameters correctly in your system, it turns out you will need very large IRSs in order to get a meaningful gain, right? So therefore, this IRS will complicate your system design. And as a result, we have to come up with scalable descriptions of the IRS, right? Maybe in terms of what we proposed, right? Or what maybe also what others proposed. So in terms of scalability, that you do not just add more complexity, but you get a gain at a low complexity, right? So I mean, a good example are actual relays, right, that were mentioned before. So if you look at relays, right, I mean, how many papers have been written about relays, right? I mean, tens of thousands of papers, right, have been written on relays. We all wrote them, right? So including myself. But then if you look at where actually relays are used in practice, right, it's negligible, right, in comparison. So, you know, there are very few systems that really rely on relays and that use them extensively. And I think one reason is just that because it adds so much additional complexity to your system compared to the gains that you can realize, right? So, you know, we have to be careful not to basically,
Yes.
and of course we cannot answer this now, right? I mean, whether this will be the same with IRS, right? We can just investigate, and then in the end we will find out whether it's so or not, right? But I guess this we should keep in mind, yeah.
Okay.
So I'm aware that I couldn't fully answer the question, right? But I think it's too specific for me. Yeah.
Okay, another question is, main physicists claim that optical IRS should be made of gold materials. How cost efficient is such a solution?
I would assume that the amount of gold that you would need is very, very low, right? That would be my guess, right? I mean, otherwise, you know, this would be not, I guess, feasible. But yeah, I really cannot, sorry, I cannot answer the question, sorry. Yeah.
I think we have a last question. Yes, the last question is, what is the precision of the tile model for IRS? For a small tile, the boundary effect caused by the edge of the tile may not be negligible, according to the scattering theory.
Well, but that's included, right? So I mean, the boundary effects, those are included, right? So basically, the fact that the IRS has a finite size, right? This is included in the model, right? This is why you get the sink function in the end, right? So, right. So this is basically for the reflected beam, and the reason why you have the sink function, right? This comes from the finite dimension of the IRS. So you can make it as small as you want, right? I mean, that's included. I guess if you go significantly below the wavelength, maybe this becomes meaningless. But unless so in the domain in which we work, I think that part is fine, right? So this part we modeled correctly. What we did not, of course, model correctly is that we assume that this reflection coefficient tau here, right, the amplitude, is independent of the phase shift, right? Whereas in actual phase shifters that are implemented, usually, you know, if you change the phase, this will also affect the magnitude of the reflected wave, right? So therefore, this is I would say, an optimistic assumption. Yeah.
Okay. Yeah, I think we don't have more questions. Let me check. Yes. So, yeah, we don't have more questions. All questions were answered. So, Professor Robert Schober, thank you very much once again. Actually, today we have a record number of attendings. In all of our seminars, we reached around 885 participants.
Wow.
So this is a huge number.
Yeah.
And thank you very much. I know your time is very tight. You are
no, it was really a pleasure. And so thanks again for inviting me, and thank you to the audience, right, for the many good questions. So, you know, it's much more fun in the end if some people also ask questions, right? And at least it shows that they are interested, right? Rather than,
yes.
You know, if
so some
really
attendants requested the slides. So maybe
yes, I send them to you maybe, and then you can distribute them if you like. Yeah.
Okay.
I'm happy to share them.
Yeah, and the presentation has been recorded and will be available in a TII YouTube channel.
Great.
So, yeah. Okay, thank you very much. And
thanks.
Thank you our attendants. And hope
thank you
to see everybody in 2 weeks in our next Telecom seminar. Thank you very much.
Thanks. Thank you. Thanks.
Bye-bye.
Bye-bye. Bye, everyone. Bye.